Welcome back to the deep dive. You know the mission. We sift through dense, challenging material, pull out the core concepts, and lay them out so you can get up to speed quickly on what's shaking things up. And today, well, we're diving into a theory that doesn't just tweak modern physics. It aims to replace the fundamental plumbing. We're tackling Lethon Hound's unified postmodern theory, UPT, and focusing right in on its most radical idea, vacuum as physical infrastructure.
Yeah, this is definitely a take a deep breath moment. For, well, centuries, really, we've thought of the vacuum space as just an empty stage, passive, a geometric background for everything else.
Right, where physics happens.
Exactly. But UPT flips that completely. It says, imagine the universe isn't a stage. It's more like a vast, continuous ocean, an active field. And that field, the vacuum, is the physical infrastructure. It's not nothingness. It's maybe the most important thing there is.
Okay, that gives us something solid to picture. Like if space is more like water or maybe a kind of universal jelly, then light, particles, movement, they're all just effects in that jelly.
That's the core concept, yes. Ripples, structures, variations within that underlying medium.
So our goal today is to unpack the 5 big ways UPT shifts things. And, critically, look at the actual testable predictions it offers. Because that's how we move from, cool idea to potential science, right?
Absolutely. It has to make predictions that differ from current models. We need measurable differences, experiments where established physics might fall short under specific conditions UPT describes.
Okay, let's jump into maybe the most unsettling idea first. The one that seems to pull the biggest thread from established physics. UPT claims the speed of propagation, what we normally call the speed of light, is local.
Yes. That's point 3 in the UPT framework, and it's the seismic one.
Yeah.
The theory states propagation speed isn't a universal constant in the strictest sense. It depends entirely on the local state of the field.
The local state, meaning?
Specifically, its intensity, I, and its immediate environment, the gradient. The idea of a single, unchanging speed limit for the universe. UPT argues that's an approximation. A very good one, usually.
Hold on. But that's the cornerstone of relativity, isn't it? If you say light speed can vary locally, how does UPT even begin to mesh with all the high-precision physics we verified? Doesn't that just break everything?
It forces a reinterpretation, maybe not a complete demolition. UPT would say that for 99.9% of the universe we observe, the vacuum field is incredibly uniform.
Yeah,
so the variance in speed is negligible, and treating it as a global constant works perfectly.
So relativity holds as an excellent approximation in most cases.
Exactly. But UPT predicts that in specific situations, maybe near extreme gravity or in carefully engineered environments where the field intensity changes sharply, that local speed will measurably change. And that demands new kinds of experiments, which we'll definitely get into.
Okay, fascinating. So if the speed depends on the field state, let's back up. Define this field. What are points 1 and 2 about space and matter itself?
Right. So point 1, the vacuum is a continuous internal field. The key shift is thinking of space not as the container, but as an attribute of the field. Like wetness is an attribute of water. And this leads right into how UPT sees matter. Particles, or hot as their term, aren't fundamental little balls. They're just organized, stable regions within this continuous field. Local structures in the ocean, not separate things floating in it.
But hang on, if they're just field structures, why do they seem so discrete? Why do we measure distinct mass, charge, all that? That feels conceptually fuzzy compared to point particles.
That's a really sharp question. And it ties into point 4, which we'll get to, about interaction. The discreteness we observe doesn't come from the field itself that is continuous. It arises from the way things interact.
How so?
Specifically at the boundary. Interaction, UPT says, involves quantization at the border of these organized field regions. Think of a wave hitting a wall. The water is continuous, but the interaction at the wall is sharp, defined. The effect is discrete.
Ah, okay. So the underlying reality is continuous, but the measurable interaction gives rise to the discreteness we see.
Precisely. And that flows into point 2. Waves as intensity variation. Light, radio waves, any EMR. It's not particles shooting through emptiness. It's just the propagation of changes, variations in the field's intensity.
Like a ripple spreading across that jelly we mentioned earlier.
Exactly. A vibration or a tension fluctuation moving through the medium itself. No need for photons as separate entities traveling through space. They are the traveling variation of the field space.
And if that's true, the implication is, wow, you could potentially engineer the medium itself to control how energy travels.
That's the potential technological payoff, yes. designing the field state, not just the signal going through it.
Okay, let's transition then. How does UPT actually describe these interactions, and what does it say about the geometry, the math we currently use?
Hmm.
You mentioned the border. That's point 4, right? Surface boundary interaction.
Yes, this is key for explaining things like reflection, refraction, absorption. UPT proposes that all physical interaction happens right at the surface boundary, where a field variation meets the edge of one of those organized regions, like a particle or an object.
And what governs that interaction?
A principle called surface intensity balance. Basically, the field intensity has to balance across that boundary. How it achieves that balance determines how much energy gets transmitted through, how much bounces off, reflection, and how much gets absorbed.
So it's about balancing intensity locally at interfaces rather than, say, force carriers acting across a distance.
That's the picture, yes,
Yeah.
which leads directly to point 5. Geometry as a tool. All the math we use, Euclidean, Riemannian geometry describing paths, light takes, orbits, etc. UPT says it's incredibly useful, obviously. We built modern science on it.
Well,
But it's a secondary tool, an effective description that works incredibly well, but only under specific conditions.
which conditions?
When the field gradient, the change in intensity over space, is very small, UPT actually puts a number on it. This geometric approximation holds when a specific small gradient parameter is less than about 0.01.
Ah, okay. So there's a threshold.
Exactly. And importantly, this threshold covers almost all everyday situations in classical experiments. It explains why Newtonian physics and even relativity's geometric approach have been so successful. They operate within that small gradient regime.
But if you go beyond that threshold, say in highly controlled lab settings with steep field gradients.
Then UPT predicts the simple geometric path description will break down. You'd need to use the full field description, the field-based knowledge, or FBK, based on I and its gradient, HI. Geometry becomes just an approximation that's no longer accurate enough.
So what's the big win here? If the old math works 99% of the time, why go through this conceptual overhaul?
Unification. The real power, proponents argue, is that UPT describes everything: wave transmission, reflection, refraction, diffraction, boundary interactions, using just those two core variables, field intensity
Die.
and the spatial gradient.
One language for all these different phenomena.
That's the goal. If you can describe all that diverse physics with just I and Ri, that's a huge simplification and unification of our understanding.
Which means if you, listening, can really grasp intensity and field gradient, you've basically got the keys to understanding this whole framework. Okay, now for the crucial part, the proof. How do we test this? What are the specific make-or-break predictions?
Right, if UPT is just a neat story, it's philosophy. To be physics, it needs testable predictions where it clearly diverges from established models. UPT outlines 3 key ones.
Prediction A. What's that one about? Sounds like it tackles wave interference.
It does a two-path interference. Imagine a standard dual-branch interferometer. You split a beam, send it down 2 paths, then recombine them. UPT predicts a specific phase shift, delta phi, when they recombine.
Okay, standard interference gives phase shifts. What's different?
What's different is why. UPT says this phase shift depends not just on the path lengths, but critically on the configuration of the field gradient Irchai between those 2 paths. You could have 2 paths as identical geometric length, but if the field state along them differs in a specific way, UPT predicts a phase shift that classical optics wouldn't.
So manipulating the field between the paths should change the interference pattern, even if the geometry doesn't change.
Precisely. And UPT sets a high bar for verification here. The difference needs to be repeatable and statistically significant to at least 5 sigma.
Phi sigma. For listeners, that's the gold standard in particle physics for discovery. It means the result is extremely unlikely to be just chance. So they're demanding serious proof.
They are. No ambiguity allowed.
Okay, what about prediction B? This sounds like it hits the speed question directly.
It does. B. Varying media transmission. This focuses on time of flight, PTOF. UPT predicts that if you can precisely control and measure the field intensity and gradient within a medium,
Like a special gas or crystal, maybe?
could be, yes. The time it takes for a wave pulse to travel through that medium should change based on those controlled field parameters. And crucially, this change should be independent of and not explainable solely by the standard geometric refractive index of the medium.
So you change the field state, not the material density or composition, and the travel time would still change.
Exactly. That would be direct evidence that propagation speed is governed by the field infrastructure itself, not just the material properties as we usually model them.
And the final one, prediction C. Sounds like it's about checking the limits of our current models.
Pretty much. C. Mapping effective lenses. This is essentially a check on when the geometric approximation point 0.5 holds and when it breaks. It requires experiments to show that calculated geometric paths, the extremal paths, match the observed behavior only when that field gradient is below the threshold, that naimetric less than 0.01 value.
And when the gradient is steeper.
Once you engineer a situation where the gradient exceeds that level, the observed path of energy or light must deviate measurably from the simple geometric prediction. You'd need the full UPT field calculation, I and high, to match reality. It's about mapping the precise boundary where our geometric optics start to fail.
And UPT is apparently quite strict about how these experiments should be done. There's an open research program?
Yes, transparency and reproducibility are central. UPT calls for using standardized setups, like that dual-branch interferometer or specific slow gradient chambers. But the non-negotiable part is open access.
Meaning?
All raw data and the analysis code used must be made public. The goal is to allow any lab, anywhere, to replicate the experiment and the analysis independently. If results can't be replicated, the theory, or at least that specific claim, fails.
That seems fair. What else?
Another key point is about the parameters within the theory itself. Things like, say, a factor linking field intensity to propagation speed, or how intensity affects phase. UPT insists these parameters, these K-values, must be derived directly from the experimental measurements.
Not preset or assumed?
No. You can't tweak the theory's constants to fit the data afterwards. The constants must emerge from the data. It keeps the theory grounded in empirical results.
This sounds like it needs a whole village. It's not just physics, is it?
Oh, absolutely not. It's
Yeah.
massively interdisciplinary.
Yeah.
You need physicists for the core interference and timing tests. You need material scientists to design specific boundary interfaces to really test that surface intensity balance rule.
Right.
You need engineers to build sensors that can actually measure the field state I and Harris accurately in real time. And you need mathematicians to help formalize the limits of the geometric approximation. It's a really broad effort.
Okay, before we wrap up, let's hit a couple of those big nagging questions. The elephant in the room, maybe? If this is right, what about, say, particle physics? Where do particles go in this field view?
Yeah, the particle problem. UPT's answer, based on the materials, is that particles aren't fundamental things, but stable, organized structures of the field itself. Mass, charge, spin, these are properties of these stable field configurations.
And the quantum effects, the discreteness.
That arises, as we touched on, from the interaction mechanism at the boundary of these structures. Quantum mechanics describes the rules of those boundary interactions, not necessarily the underlying continuous nature of the field. It shifts the focus.
Okay. And the speed of light constancy. We talked about it being local, but what about cosmology? Doesn't that rely on a constant?
UPT suggests that while speed is locally variable on the largest cosmological scales, the universe appears remarkably uniform. In that generally uniform field, the propagation speed would be effectively constant, consistent enough for current cosmological models to work as good approximations. The variation matters most in specific, non-uniform conditions.
Got it. So let's talk payoff. If we can actually control this vacuum field state, what are the potential benefits for us societally?
Well, the main thrust seems to be around enhanced control and sensitivity. Imagine sensors for gravity, EMR, whatever, that are far more sensitive and less noisy because you can actively manage the field state around the sensor itself, stabilizing the medium.
Quieting the background noise, essentially?
Something like that.
Mm.
Then there's energy and information transmission. If you can tailor the field state along a path, maybe you get much more efficient transfer, especially through complex or noisy environments. Think better fiber optics or clearer deep space communication. And fundamentally, it offers a framework for local measurement and calibration. Technology becomes less reliant on assuming global constants everywhere and more focused on measuring and potentially controlling the local conditions.
So moving from just optimizing the signal to actually optimizing the space the signal moves through, which, yeah, brings us right back to the core idea we started with, the vacuum. Not empty, but active infrastructure, all unified by intensity and its gradient.
It really is a profound conceptual shift if it holds up, moving the focus from the geometry of paths through space to the dynamics of the underlying field that constitutes space.
And that leaves us and you listening with a final thought to really chew on. If UPT proves out, if energy and information transfer efficiency really is tied to controlling the vacuum field state, I mean, what fundamental limits could we break in computing, sensing, maybe even propulsion? What becomes possible if we can genuinely start to engineer space itself? That's definitely something worth mulling over. Thanks for joining us for this deep dive. We'll see you next time.